This is a lecture on printed circuit board fabrication, and this lecture just covers the material design and manufacturing process for conventional printed circuit boards. So these are your most typical printed circuit boards that are used in most applications. Um, there are many different types of printed circuit boards and all kinds of particular applications, and I'll mention some of those. But if this topic really interests you, there is a advanced electronics manufacturing class that Dr. Pan over in IME, over in the IME department teaches. I believe it's IME 457. So that class goes into a lot of the particular types of printed circuit boards for various specific applications. But again, this lecture is just for your most typical type of printed circuit board that's used in a wide variety of like general type of applications. So your materials, your basic materials for printed circuit boards are you have a substrate material which provides mechanical support and some heat dissipation. This is the board itself that provides the platform for the components to be affixed to. Your most conventional board, the substrate material is fiberglass. Now, one special application is if you have some type of device where you're really limited for space. Sometimes flex boards are used where the substrate is a film material. But again, the most general type of printed circuit board, the substrate is a fiberglass. And the most popular fiberglass board is an FR4. FR stands for flame retardant. They actually add a chemical called bromide to the fiberglass to give it this resistance of heating up and possibly flaming. And there's various types of boards with different ratings, like there's FR5, FR6, and so on. The higher the number, the more flame retardant it is. So basically, the more of that bromide material that's put within the fiberglass. But the FR4 is the most popular because it gives good resistance to possibly burning up and starting a fire, and it's at a good value. It's at a good price for that amount of protection. Okay, so you got your substrate. Then there's the conductive material, which are your electrical connections. Most often that material is copper because it's lightweight. Also, it has good conductivity, electrical conductivity, and it's at a good price. Silver and gold are better electrical conductors than copper, but they cost more. So usually, again, copper is used because it's the best value. Now, there is a specific application in microwave applications where you're dealing with circuitry at microwave frequencies, which is a really high frequency, where they may have gold-plated traces. Okay, and the reason for that you'll learn when you take your high frequency classes later on in the curriculum. And then the two most common, although nowadays by far the most common is this of these two is a double-sided board. This is where copper's on both sides. I'll show you an example coming up shortly. But there's also boards where you just have copper on one side, and that's a single-sided board. And then a more advanced topic is printed circuit boards that have multi-layers, more than 2 layers. But we don't go over boards like that in this class since it's a basic class. But again, in that advanced class that Dr. Pan teaches, IME 457, there a lot of time is spent on boards that have more than 2 layers. So let me show you a board that I have here. So here's a board that's an FR4 board. So again, the board material, and you can see it's about a 16th of an inch thick. This is the fiberglass. And then the lines that you see, those are the copper traces. Okay, and this board does have traces on both sides. So this is a double-sided board. Okay, now another material for a printed circuit board is the solder mask, and it's a plastic coating. And the main purpose of this plastic coating is to prevent solder bridges. Okay, because solder flows, and it likes to flow where it shouldn't be. And if you have solder between, say, two pads or two traces where it shouldn't be, it causes a short, which is what we refer to as a solder bridge, and that can cause damage to your circuitry. So the solder mask is to keep the solder in place, okay, where it should be. And it's the solder mask that gives the board its color. So additionally, the solder mask makes the board look nice. It also increases your corrosion and flammability resistance somewhat. But again, the main purpose is to prevent solder bridges, so preventing the solder flowing to where it shouldn't go. Also, in addition to the solder mask, there's an ink layer which is called the Silkscreen, and the purpose of the Silkscreen is to do several things. One is to provide reference designators. The reference designators shown in this picture here, C2 is a reference designator, D1, T1, C3, C4. And these reference designators are there just to make it easier to inspect and also troubleshoot the board, because you can use these reference designators to see how the component should be connected in the circuit by referring back to its schematic. That these same reference designators would be in the schematic, by the symbol that represents this physical component on the board. Also markings for polarized components like diodes and some capacitors are on the board. So here, see how on the board there's a band, so you match up the band on the diode with the band on the board to make sure that diode is oriented correctly. And then if a capacitor is polarized, often it will have a plus on its physical body or near a lead, and you want to match up the plus on the capacitor itself to like this plus designated on the printed circuit board. Okay, so you put the capacitor in correctly. And then also on your Silkscreen layer, the ink layer, you'll have component values. So you can see here the capacitor values, 10 microfarad, 100 nanofarad. Yeah, and if there's no resistors in this case, but if we had resistors, it would show the resistor value. So let me go back to the board I showed you earlier, and you can see here again there's a Silkscreen with reference designators. See, here are some ICs with designators U, U4, U3, U2, and so on. It also has, in some cases, the particular IC 74LS86. Here's another board just to show you that you can get boards of different colors. Again, the color, the solder mask is what gives the board the color. So here's another board that's double-sided, blue board, again with some Silkscreen capacitors, some resistors here, R1, R2. Okay, here's a board from IME 156. Okay, also has a bunch of different markings on it. And here's a board from Osh Park. Osh Park has purple boards. It's part of their marketing. So just some various different boards that I have laying around. Alright, well, PCB design is done with computer-aided software or computer-aided design software, CAD software. You'll be using Eagle. These are some others that I have used in the past, but there's many other software packages that you can use to design printed circuit boards. So no matter which software you're using, there's these three basic steps. First, you enter the schematic, and then once the schematic is entered, just by clicking a button, the software will take that logical representation of the circuit, with the symbols and how they're connected, and convert it into a physical representation onto your computer screen. So it will show the physical components along with how they're connected with these lines that are called nets. And then the next step is component placement. So you'll place those physical components on your computer screen within a certain area that represents the printed circuit board. And then the last step is to do what's called routing, and that's changing those nets that are the logical connections coming from the schematic and turning them into physical connections that are going to actually be the copper traces on a manufactured board. Now there's a couple of different verifications to do in your design before you get your board manufactured. One is DRC, which stands for Design Rules Check, and this is just to make sure that your PCB design can actually be manufactured. Okay, that's what this design for manufacture principle is all about, and it seems pretty obvious, but it's important before you send your design to a manufacturer like Oshpark that it can actually be manufactured, that there's not something in your design that's not possible as far as manufacturing goes. So what the DRC verifies is that your design meets the criteria that you input to the software. So for the lab, the EE143 PCB design that you'll be doing, now you're not doing a DAC design, you're actually doing continuity tester design, but we still want you to use these criteria that we have listed here. You want 10 mil trace width, 10 mil trace separation, and 20 mil drill hole diameter. Now a mil is 1/1000th of an inch. Okay, so 1 mil is 0.001 inch. Another useful conversion is over here. A millimeter is a little over 39 mils. So you'll input this criteria to the software, and then when you run the DRC, it will check to make sure that your design meets this criteria. Okay, that you don't have a trace width that's something different than 10 mils, and you don't have a trace separation that's less than 10 mils, and that your drill hole diameters are meeting the 20 mil criteria. And if something's violating these checks, an error message will be outputted, and then you'll have to go in and make the correction. Now there's another verification in Eagle that I didn't list here that's called ERC, and that stands for Electrical Rules Check. And when you run the ERC, it checks your connections on your layout to the connections in your schematic. So it makes sure that that your design, your printed circuit board design, is actually connecting the components as the schematic specifies. And again, if there's a discrepancy, an error message will be outputted, and you'll have to fix it and recheck it again. Now, when you watch my intro video to the lab where you do the PCB design, you'll see that I also want you to do a manual check. Even if both of these checks check out okay, even if the software says your DRC is good and your ERC is good, I still want you to manually check your schematic against your layout. So just manually go through and check each trace is representing the proper connection in your schematic. Okay, because the software checks, they're not 100% foolproof, and you just want to make real sure, double, triple sure that your layout is actually representing the schematic, because it's much easier to make a correction before you get the board manufactured than make the correction after. Okay, so it's worth the time just to, like I said, double, triple check that your layout is actually matching what the schematic is showing. Okay, here are the electrical concerns that we have with a printed circuit board. A big one is making sure that your traces can handle the amount of current that it needs to. If you try to pass too much current through a trace, it's going to overheat and possibly lift from the board. In the worst case, it could actually start flaming the board. Also, you want to make sure that there's no arcing between your traces. Okay, the closer traces are, the more susceptible they are to arcing. And then also for high frequency designs, the separation also has to do with how susceptible to interference, what's called crosstalk. Now, in this class, we don't have to worry about this. We're not dealing with any high frequencies, but in the future, it's quite likely you may have something that is operating at a frequency more than 30 kilohertz, and you'll have to be concerned with this. Okay, here's some data for an FR4 board that has 1 ounce of copper. And what 1 ounce of copper means is that that's the amount of copper per 1 square foot of substrate. Again, I have down here a mil is a thousandth of an inch. So this data shows for this particular board, what kind of voltage you can have between the traces and not have to worry about arcing, for a particular separation. So you can see here that if you have 25 mil trace separation, well, you can have a difference of 150 volts across the traces and it shouldn't arc. Okay, for 50 mil trace separation, you can go up to 300 volts. Okay, so the wider or the further apart you have your traces, the more voltage you could have across those traces without having an arcing issue. And then down here it shows the data for current, the amount of current you can handle, maximum amount of current you can handle for a given trace width. So 5 mil, half an amp, up to half an amp, 10 mil up to 0.8 amps, and so on. So the wider the trace, the more current you can pass to that trace. Okay, also some electrical concerns with a printed circuit board. We have what's called a copper pour and also a ground plane. Now, in my intro video to the lab, I believe it's lab 4, where you do the continuity tester printed circuit board design, I mentioned how Jeffrey Blum, who has a couple of videos on Eagle, okay, how to use Eagle. Well, in those tutorials on Eagle, he mentions a copper pour and a ground plane. But for the continuity tester design you're doing in the lab, there's no reason to have a copper pour or a ground plane, because as you see here, copper pours are when you have components that dissipate a lot of heat. The copper pour will help dissipate that heat. It acts like a heat sink. Ground planes, a ground plane is necessary when you have a high frequency design, and the ground plane helps reduce interference. But we don't have to worry about either one of these for the continuity printed circuit board design, so I recommend that just ignore this in the videos. But here in the lecture, it's good to know what these are for. Also, let me show you a board that does have a copper pour. This IME 156 board here. See these patches of copper that are adjacent to the traces. See the lines of the traces, but then when you don't have traces, there's these big patches of copper. See on both sides here, like there's a trace, and surrounding the trace on both sides, here's a big patch of copper. Those patches of copper, those are that's what's referred to as the copper pour. And again, they're there to help dissipate heat. Compare that to, see this board here. This board here doesn't have a copper pour. That in between all the traces are just the substrate. Okay, there's no patches of copper in between where the traces are. Alright, so let's talk about how a printed circuit board is actually manufactured, okay, the process that's involved. And first you start off with panels of raw copper. Okay, these are panels that just have, well, most typically you'll have double-sided boards. So this is raw double-sided board copper. And when places like Osh Park manufacture a board, they don't do like each individual board separately. What they'll do is they'll put a whole bunch of boards onto a panel, a panel about the size of what you see in this picture. So when you send your order, when you send your printed circuit board design to get manufactured at Osh Park, and this would be true of any of the PCB manufacturers, they put your design in a queue until they have enough to fill out one of these panels. So typically what Oshpark will do is that, you know, they'll send you an email once they've received your order, but then they'll send you another email when they actually start the process, okay, when they actually have your board on a panel. My experience has been that it usually takes about 2 or 3 days after they receive your order to actually get your board on a panel. And of course they do this just for efficiency, right? It's more efficient to do a whole bunch of boards at once as opposed to doing each individual board by itself. Okay, well the next step in the process is that they'll drill the holes for the through-hole components and your mounting hardware, and also vias. And and as I have here, vias, they're just electrical connections between layers. So this picture here shows, you know, a printed circuit board that's been cut, just so you can see the via here. The via is through plated, okay, through an electroplating process. There's copper that's put between the inner walls of the via, and that's what makes the connection between the layers, is that lining of copper within the inner walls of the via. In this, these holes are drilled by a computer-controlled drill, okay, and after the drilling, you know, they clean up the board by polishing it and getting rid of any rough edges. Okay, I mentioned this, that the holes, now whether it's a via or a hole for a through-hole component, is that they'll make a through-hole, which means that they electroplate copper along the inner walls. So for a via, that's what makes the connection from the top side to the bottom side. They'll also do this for the through-hole components, and that's just so when you solder the through-hole components from one side, the solder will flow to the other side through that through-plated hole. And you can see it's a very thin layer of copper that's put on those inner walls. It's a micron thick. A micron is a millionth of a meter. Okay, so it's a very thin layer. And then after the through plating of the vias and the through hole component holes are made, then they'll electroplate copper onto the panel of the board to the desired thickness. I mean, a common thickness is 1 ounce, and as I explained earlier in an earlier slide, when they say 1 ounce of copper, they're talking about the amount of copper per 1 square foot of substrate. Alright, well then the next part of the process is actually putting the image of the circuitry onto the copper, and this is done with Photoresist along with a photo tool and using UV light. Okay, this imaging process is, as you can see here, it starts with the photoresist being put onto the copper, and they use high heat and pressure to put the photoresist on. Photoresist is a material that's sensitive to UV light, and there's 2 types of photoresist, negative and positive. Negative photoresist, the resist hardens when it's exposed to UV light. Positive photoresist, which is actually used in IC fabrication, is the opposite. It actually becomes soft when it's exposed to UV light. And one thing you'll see in a couple of lectures is that when we talk about IC fabrication is very similar to this part of the PCB process. It's just with ICs, everything's at a smaller dimension. Okay, so after the photoresist is put onto the copper, then a mask is used, and that mask has the image of the circuitry that you want to have on your printed circuit board. And the photo tool is a negative of the result of your CAD software. And the UV light exposes the photoresist that goes that is on top of the transparent areas of the photoresist, and the photoresist so that's the photoresist that becomes hard, and then the photoresist that's underneath the dark areas of the photo tool remains soft. So let me show you a demo of what we just discussed. So first of all, here's a photo tool, Okay, so you can see it's just a film material like camera film. And the transparent areas, that's the circuit that you want to have on your board. Okay, the transparent areas represent the traces that are connecting the components of your circuit that you designed with your Eagle software. And this photoresist is a negative of the actual hard copy layout of your Eagle design. So your Eagle design will have the traces as a dark color, and it will have where the traces aren't as a light color, but the photo tool is a negative of that. It's just the opposite, right? Your traces are transparent, and where the traces aren't are dark. And then here's a double-sided raw copper board. See right here, that's the fiberglass and the copper on both sides. So this is FR4 board, okay, just raw stock. Okay, now here, let's pretend the blue paper is the photoresist. Okay, I'm not in a yellow lighted room. When you're dealing with photoresist, you have to be in a room where you can only have yellow light. There can be no blue light, because the blue light will actually expose the photoresist. So I don't have any actual photoresist, but you know, this blue paper we're just going to pretend is the photoresist. So the photoresist is put on top of the copper just like this, and again, it's done with high heat and high pressure to make a really good adhesion. And then the next step is you put the photo tool on top of the photoresist. So now when UV light is shown or shined into, you know, the direction here, like down onto the photo tool, well, the UV light exposes the photoresist that's underneath the transparent areas of the photo tool. So that photoresist becomes hard. And then the photoresist that's underneath the dark areas of the photo tool remains soft. Okay, so the next step is they use a developer, and the developer takes away all the photoresist that wasn't exposed, and it only leaves the hardened photoresist that's on top of the copper that eventually is going to become the traces on a printed circuit board. So now, after the developer, now these areas where the copper that we don't want is exposed, well, that copper that we don't want is etched away. Okay, an etchant solution is used to dissolve all that copper that's not underneath the hardened photoresist. And then the last step is that they'll use a household cleaner, okay, a mild astringent that removes the hardened photoresist from the copper that is where the traces are. So this bottom picture here shows you what the board now looks like after the astringent has been applied. Okay, so then the next thing is the silkscreen layer. So they put on the ink, okay, the silkscreen that has the reference designators and the polarized component markings along with the value of the components. And after the silkscreen is put on, that's when they'll do electrical testing, checking for any unwanted shorts or opens. And then the last step is cutting out the individual printed circuit boards from that panel. Okay, so that was the lecture. Now, the last thing for you to do is to watch this video. This video was made by a company, PCB Way, which is over in China, which will step through the different processes that we just talked about. And, you know, Osh Park has the same process. So this shows you how your board that you designed for the continuity tester is going to be manufactured. And as you're watching this video, there is a worksheet. Okay, this worksheet here, PCB Manufacturing Video Worksheet, that's available on Canvas. So you would just want to download this, and as you're watching the video, fill this out. And then this is a graded assignment, so once you have it filled out, upload it to Canvas for grading by the due date. Okay, well that's what PCB fabrication is about. Next lecture will be about assembling a printed circuit board. So putting the components on and then doing the soldering.